Good morning and welcome back. Earlier, I introduced the chemical potential, and the chemical potential is a really, really powerful idea that I'm going to use in at least two different ways. One of the ways that I'm going to use it, and that's where we're headed actually, is as a driving force, not as a model, as a mathematical quantifier of the degree of disequilibrium of a system with respect to mass transport or chemical equilibrium. What I mean by that is that if there's an imbalance in the chemical potential, then that means the system will continue to change and evolve until it reaches its free energy minimum or its entropy maximum. Doesn't matter which of those two ways you choose to view it. And so the difference in chemical potential serves as a drive. And so that's one of the things that we'll think about. The other idea that I will pursue a little bit is the use of the chemical potential as a way to integrate out the degrees of freedom of the reservoir. I already mentioned that Gibbs's picture of the various free energies, the Gibbs free energy, the Helmholtz free energy, and so on, was as a way to account for the reservoir and the fact that the world is maximizing the entropy of system plus reservoir. He says, well, it's a hassle to try and account for all the degrees of freedom of the reservoir. Let's just do it once and for all, and we'll give it a name, and we'll call it the chemical potential. In other words, I will once and for all account for what the free energy cost is when I take a molecule out of the reservoir and put it into my system. That's what we call the chemical potential. So in this particular vignette, I want to talk about binding reactions. And specifically, I'm asking the question, if I have a receptor, shown here in green, what's the probability that that receptor will be bound by a ligand? So the goal here is I want to compute P bound as a function of the concentration of ligand. Maybe I'll choose a better notation, as a function of ligand. And I want to know what that function is, and in fact, I already do know. I'm going to write it down. It's the so-called Langmuir binding isotherm. So that's the answer. And I'm not going to necessarily go through the details of the statistical mechanics here because I've already recorded a vignette about that which people can watch. What I'm going to do here is I'm going to redo this calculation, but now from the point of view of the chemical potential. Prior to that, let me at least give an overview of how we can use the statistical mechanics protocol in order to compute this probability of binding. Let's just take a look at this. So I claim there are two categories of states. I have my lattice. There's L ligands. So let me label that. There's L ligands. And there's also omega lattice of volume little v. Okay? And so if I want to follow the statistical mechanics protocol, the first thing I do is I enumerate the states. So what are the states? I have the set of states in which the receptor is empty and the set of states in which the receptor is occupied. All of the states in which the receptor is empty have the same energy. What is that energy? It's L times the energy of a given ligand when it's sitting in solution. In other words, I'm saying that every molecule, when it's deposited in solution, it has an energy which I'm going to call epsilon solution. I just want to remind you, even when I'm at millimolar concentrations, that means that 1 out of every 1,000 lattice sites is occupied. Remember that E. coli has a volume of 1 micron cubed, which is the same as 10 to the 9th nanometers cubed. Remember the rule of thumb that 1 nanomolar is 1 per E. coli, or 1 in a billion. That's what nanomolar means, 1 in a billion lattice sites, if you want to think of it in that language. So if I'm at millimolar, that means 1 million out of the billion lattice sites are occupied, and still the system is dilute. Only 1 in 1,000 sites is occupied, and that's the reason that I'm going to say that the energy is independent and additive. Every molecule just has an energy epsilon solution. The total energy is L epsilon solution. In this case, one of the ligands is now bound to the receptor. So that means that I've removed one of the molecules from solution. So the energy of solution molecules is L minus 1 epsilon solution. And now I also, in addition, have a binding energy Because this glue interaction between the receptor and the ligand, I'm going to assign an energy epsilon b, which stands for epsilon bound. Okay, next. The next step in the statistical mechanics protocol is to compute the multiplicities. How many different ways can a given state occur? And the answer to that for the case in which we're dilute is omega to the L power over L factorial. This corresponds to the little example I always give about if I take 20 students to the Rose Bowl where there are 60,000 seats, the number of possible choices for student number 1 is 60,000. The number of possible choices for student number 2 is 60,000 minus 1, but I'm going to call that 60,000. And so the total number of choices is 60,000 to the 20 power because every student gets to choose from all of the 60,000 seats. The denominator, the L factorial, is just noting that the students are distinguishable. Like I said the other day, I want to imagine everybody's dressed in a gorilla uniform, so that if we're looking down with a drone, we can't tell the difference between the students. And so the total statistical weight is given by the multiplicity times e to the minus beta L epsilon solution. But if you like, this is just an aside, this is not important to the discourse, but you can also write this as e to the minus beta, and then L epsilon solution, and then minus kBt times the log of omega to the L over L factorial. This thing is the entropy. So you see this emerging immediately that I have L epsilon solution minus Ts. This is the free energy. So what is this free energy idea really doing? It's saying, yeah, you may have a state of energy L epsilon solution, but there are actually many such states. And the more of them there are, the more they compete for the overall probability. So this factor up here in the free energy accounts for the fact that I have many, many states that have the same energy that are competing for the probability. Down here, I already said the energy. The multiplicity is given by this. So now I have L minus 1 molecules in solution. This is the number of ways that they can be rearranged. And therefore, the statistical weight is given by this quantity. I can put all that together, P bound. In fact, rather than writing it out, let's just take a look. That amounts to this fraction. So I sum over all the states where we're bound, which if you look at what I just wrote, you'll see that this was given by L minus 1. Sorry, I said that wrong. This is given by omega to the L minus 1 power over L minus 1 factorial. E to the minus beta delta epsilon is what I'm going to write here. This guy is omega to the L over L factorial. And then this one is omega to the L minus 1 over L minus 1 factorial. E to the minus beta delta epsilon. One thing I did is I basically took my zero of energy. So, I took the zero of energy as L epsilon solution. And that's the reason that I got, you don't see any longer a term up here of the form e to the minus beta delta epsilon. Okay, if you plug in, the results, what you're going to find is exactly what I wrote before. Again, I encourage people to go take a look at the biological binding statistical mechanics vignette that I did in 2021 version of the course. So this is what these binding curves look like, and I just want to note that this point right here corresponds to the KD. How do I know that? Because P bound is equal to L over KD. I'm getting sloppy with my notation. I'm not going to write the square brackets around it. Note, if KD is equal to L, that implies that P bound is a half. So there's a really great interpretation of KD. KD is the concentration at which the probability of being bound is a half. Another way to say it is KD is the concentration at which the entropy term is exactly equal to the binding energy term. And the way you can see that is by looking here, where I if I am in this case where this state has statistical weight 1 and this state has statistical weight 1, the only way that can be true is, sorry, what I'm trying to say is that I'm looking for the case in which the binding energy exactly balances this. And the reason that that's important is that that means that the energy and entropy have the same magnitude. Okay. So that's basically what I want to do with respect to what we've already written down. Now I want to use the chemical potential idea. So here's what the statistical mechanics protocol looks like in the context of the chemical potential. Here I have my receptor, and there are no ligands bound, and I assign that a statistical weight of 1. Now I have the case where there's a single ligand bound on the receptor, and that has this statistical weight, and I want to try to explain why that is. So the way to think of this is that I pick up energy epsilon b, and the number of particles in the reservoir, the number of molecules in the reservoir, goes down by 1. Why is that significant? Because remember that mu was defined as the free energy when I have n plus 1 minus molecules minus the free energy when I have n. And so, as I said before, the cleverness of this, what Gibbs says is he says, well, I don't have to pay attention to the reservoir. I can account for it by defining this quantity known as the free energy. So now we're ready to write P bound. So I will do so. So P bound is equal to e to the minus beta epsilon b minus mu over 1 plus e to the minus beta epsilon b minus mu. Now use that mu is equal to mu naught, or better yet, let's call it epsilon solution. Epsilon solution plus kBt log concentration of ligand divided by the reference state concentration. What we'll end up finding is that this thing gives us L over L naught e to the minus beta delta epsilon over 1 plus L over L naught e to the minus beta delta epsilon, where I've defined delta epsilon as being epsilon b minus epsilon solution, exactly as before. And you can also note that this implies that Kd is equal to the standard state concentration e to the beta delta epsilon. That's kind of fun. So let's remind ourselves of something. Kd, the better something binds, the smaller Kd is. Kd of nanomolar means that the ligand binds more tightly than Kd of micromolar. Does this work? Well, delta epsilon is negative. So if L0 is 1 molar, then the more negative delta epsilon is, the smaller Kd is. So the sign of the Kd jibes with our expectation and our intuition. All right, so what have we accomplished? I wanted to give an example of the use of the chemical potential. I gave such an example in the context of binding reactions. So that was the point of this exercise.